You ready? Oh, you need quiz? We can have quiz at the end. I just need. I prepare one, but we don't need to do it. You ready? We start at 11. Any question before we start? Who did not do the homework yet?
I've done it, but I'm getting negative score.
Okay, I don't think C value is negative.
But yeah, that's what.
Okay, let's discuss about homework a little bit. So, Victor, what do you get for the homework?
I get values, but I have a question about the friction factor.
Friction factor.
Because if I'm doing the first part, should I use the equation of 0.046?
That is acceptable. Blase's type equation is acceptable if we want it to be very accurate. We need Colebrook-White equation.
But even if I'm taking Reynolds numbers that are below of 2000.
Don't take the Reynolds number that's below 2000. If you do laminar flow case, take the Reynolds number that is less than 2100. If you do turbulent flow case, try to take Reynolds number that is above 4000, at least 4000. Okay, yes, question? You get negative value. Isaac got negative value too, so maybe you want to talk to him. Hong, how about you? How's the homework? It's not due yet, so you don't have to start it yet. But it's just, you take this one question out too. It can take some time. Isaac is done already. Alright, if you have more questions about that, we can meet after the work. Today we're going to talk about slug flow, more on slug flow. So on slug flow, we talk about why should we study it. The main objective, right? The main objective is to get pressure drop, okay? And that's used for subsea pipeline, horizontal well, okay, or general production. And slug flow is happen likely in slightly inclined pipe. You already know if we have like just 0.5 degree upward incline, we can have slug flow. The first model that we talk about is Dukler-Hubbard model, which is strictly for horizontal flow, right? If we incline it and we use Dukler-Hubbard, it will give us some result, but it won't be as accurate as the model that we're going to talk next. Now let's wrap it up and discuss how do we use Dukler-Hubbard model to do calculation. Dukler-Hubbard model requires HRLS. Do you recall what is HRLS? Yes, what is HRLS?
Liquid slug hole.
Slug hole up in liquid slug, correct. New Hertz, that is slug frequency. We may not use slug frequency. If we don't use slug frequency, we have to use L sub S, slug length. Okay? Alright, the way that we do Dukler-Hubbard model is first we specify the input. Okay? Reynolds number, superficial Reynolds number, and mass flow rate. W sub L, W sub G. Mass flow rate is just volumetric flow rate multiplied by density. Okay. After that, we need slug frequency from closure relationship. Okay. This is a formula that we enter something in, then we get a result. Okay. That slug frequency is from closure relationship. This means that it may not be correct. Okay. It's as correct as people have. Okay. But for your case, it can be something else, especially if you deal with oil or high viscosity oil or emulsion flow with gas. It can be something else. Okay. The next one, and it can be dependent upon pipe diameter. Okay. So then we can calculate mixture velocity, right? Then we calculate the Reynolds number based on liquid slug, that formula. get C0. C0 basically is take 2 for laminar flow, 1.2 for turbulent flow, right? And we have VTB calculation. Do you still remember how do we get VTB?
C0 times ES plus
Drift velocity. C0 Vm plus drift velocity. Then we calculate X. X is what? Relative velocity multiplied by some kind of OR. What time is it? Oh, okay, it's 5. Yes, it is. So you're not late. So it's relative velocity multiplied by rho up equal to relative velocity multiplied by rho up. Or VTB minus VLTB multiplied by HLTB equal to VTB minus Vm multiplied by HLRS. We can have this, and of course you have to multiply by area and density to get X, right? To get X is pickup rate or shedding rate of liquid. Then we calculate film length 3.110. That is the equation based on mass balance with several assumptions that we discussed last time. Do you recall that? 110. Okay, that's what this is. Oh, no. It's LU minus LS. Okay. All right. Then the way that we show Dukler-Hubbard calculation is not exactly the same like the one in the book. Okay. We will review the one in the book too. This is what I suggest. Okay. It's not. This doesn't do anything like trial and error. No, I don't do trial and error. So we assume the length. Oh, this one is actually the one in the book. Assume the length LS. Okay, slug length. Or you may use 30 diameter. Okay. In the book it suggests okay, assume LS. Calculate the film length, then solve the first order ODE, right? dH by dZ. After we solve that, we get profile, film profile, height at every location. Then we calculate hole up in the film zone, velocity inside the film. Okay. Then we can recalculate LS based on the mass balance. Okay. If the LS from the mass balance doesn't match with the input LS, we do it again. Okay. We take the new value of LS, do the calculation of film profile, then keep iterating, okay, until it's matched. And after we get the film profile, after we have everything converged, then we can calculate pressure drop. Okay. Delta P sub A, what is delta P sub A? Isaac. Delta P sub A is? Okay. Pressure loss due to acceleration. Okay. And we have delta PU, okay, combination between acceleration of pressure loss and frictional pressure loss. Then we're done, right? Okay. What is the restriction of doing this? If we use Dukler-Hubbard model, number one, horizontal only. Okay. The accuracy is dependent upon this VTB. Okay. We may do everything right, but if the closure relationship that we use doesn't give us the right result or accurate result, we don't get the correct answer either. Okay. So it's sensitive to closure relationship, VTB. Also this, 2 and 1.2. Okay. That C0 is a distribution parameter, right? That distribution parameter has to do with the velocity profile inside the slug body. Okay. So right now, 1.2 comes from the case where everything is uniformly distributed correct? If we do it for high viscosity oil, like in the lab downstairs, is it uniformly distributed? Not really. We have like, okay, big bubble stay a little bit more on the top, on the bottom we have less gas or something. So it's not quite uniformly distribution. Then 1.2 may not be accurate. Okay. So every closure relationship that we use impact the pressure drop result. Okay. We have closure relationship for frequency. Okay. What if it's not right? Slug frequency depends on where the location away from the inlet. Okay. But the closure relationship may be for fully developed flow. So this may not be fully applicable. Okay, so be aware of this. Right. Other than that, this model is a good model to start with. The next one is more difficult. Okay. So to solve this, we have to match W sub L. There are several ways of doing it. Okay. One way to do it is this one. So this one I show you how I did it. So the way I do it, okay, we specify the pipe condition fluid property. Okay. Calculate VM, pipe area, flow rate, mass flow rate, superficial Reynolds number based on VSG, VSL. So we get those numbers. So those numbers tell me that this could be turbulent flow. Actual Reynolds number, is that going to be more than that or less than that?
More.
Okay, we will see if it's more or not. Okay, I think it's more. So based on those, we can select C0. Okay, calculate VTB, C0 VM, and drift velocity. Alright, substitute the value in, get VTB. Oh, everything here is for incompressible flow. Velocity has to be a lot less than speed of sound. Okay, so like 20 meters per second is like kind of limit. Okay, if we, especially for liquid phase, if we do like 30, 40, and the answer may not be valid. Okay, so what I'm saying is this kind of thing is not for flow across a choke. Okay, flow across a choke is completely different from this. This is for incompressible flow. Okay, velocity is a lot less than speed of sound. All right, calculate HLOS. I use Gomez et al. Closure relationship. Get the value of HLOS. Calculate X value. Delta V, rho A, HOA. Get the value in kilogram per second. Assume. Okay, this is the step that can be different. Here I assume 30 diameter. Okay. You may indeed use frequency. Option 1, use frequency. Option 2, use LS, closure relationship. Okay. If we use frequency, we do something similar to this, but a little bit different. Okay. The one that uses frequency is in the book. So we plot this part to find the critical level, the denominator, okay, plot the denominator versus H2 Find out what H2 cause the critical level or slope equal to 1 infinity. Then the starting point has to be lower than that. Okay, this is a corrosion relationship for slug frequency. Substitute the value, I get that Lu is VTB over nu or 2.77. Okay. Next step. This part is not exactly the same as the original Dukler-Hubbard, but basically it's the same thing. Calculate HLOS. Okay. From the HLS, I use Newton method to solve for H2 law. Okay. Why do you need Newton method? Why is that? Isaac?
To find the
To go from capital H to small h, why do I need Newton method?
because
Okay, very good.
because the variable that we want is implicit in the
It is implicitly defined. It's not unknown equal to whatever expression on the right hand side. Okay, we have known value HLS get from previous step, right? HLS from that closure relationship, that HLS, and on the right hand side, I have the unknown stick everywhere, over there, over there, over there. It's not like H2 dot equal to something. This is some constant equal to some expression of H2 dot. So you can use some other method. For example, what is a good example? How about fixed point iteration? Yeah, you may try that. Bisection method. Or if you do it offline or not during the test, you can use a goal seek. During the test, what is an acceptable approximation? HLS equal to H2 though, that is fine. During the test, that is fine. You're not going to use Newton-Raphson to do anything like that during the test, right? Unless this is a numerical method test, then we want that. But okay, you can assume it's the same, but keep in mind that it's not. Okay. Then HF at z equal to 0 can be obtained. Alright, I got that. Look at that value. 0.4696, 0.4761. Pretty close. So it's good. Alright, then use RKF45 to solve for it. The big expression for Dukler-Hubbard model. Use it, I get those dots, 0 dot. Okay. Calculate HRTB based on at each Z, based on HF from this one. Geometric relationship, right? Geometric relationship was in the book. It is in the book, so we can use this. Once we know HF, solve use RKF45 with the HDZ equation. We know height at every location. From height, we can calculate HRTB quickly. Okay? Can you do it quick in your calculator? Just a matter of click. Did you, who have not programmed anything in the calculator yet? How did you try? Oh, in the exam, especially final exam, please have it ready. Yes? Yeah, okay, you can try more and put more equation in there. Final exam is closed book. Okay, one cheat sheet. And geometric relationship is not given. You have to write it in. You have to write it down in the paper and go in there, right? Alright. Then I can calculate velocity. Okay. Oh, wait a minute. Before I do this step, okay. I have to make sure that we have mass balance. Okay. But we can do until the end and do mass balance. Okay. I think this one I did it until the end and do mass balance. So I calculate velocity, VLTB, velocity of liquid phase in Taylor bubble zone or in the film zone. I think that is VTB without L. Okay, that is typo. How do I know that? Delta V multiplied by whole up equal to delta V multiplied by whole up, right? Alright, so that is just VTB, not VRTB. Then I get velocity at every location. Once I get velocity at every location, I can multiply that velocity with HOA at each z value. Okay. Then I try to do this kind of integration. Okay. Integration of 0 to LF of VLTB, HLTB. That is part of mass balance equation, is it? Is it not? Which one is that? Okay, WL. So you see this one? Oh, every one of them require that kind of thing, right? VLTB, HLTB. I try to do mass balance and I try to find out if the input parameter that I put it in have mass conservation or not. The output of WL equal to the input WL or not. Okay. I do the integration from 0 to LF. Okay. Do space integration. Use trapezoidal method. Trapezoidal method has to do with trapezoidal shape. Okay. You see that green trapezoidal shape, or red and green? Red one and green one over there. The formula is 0.5 multiplied by the gap. Okay, the gap delta z multiplied by the summation of the parallel height, right? And I try to do that integration, so that is the height v multiplied by h. Okay, so this is v multiplied by h and zi, and v multiplied by h at zi plus delta zi. Okay, to get one area. So this give me small integration. I add them together, I can get the whole area under the curve of the plot V. Basically, after I do everything, I get that. And that is part of the mass balance. Bonus here is if I use RKF45, okay, my trapezoidal method is actually better than second order method. Typically, trapezoidal method is not that correct, okay, but it is very good when we discretize more, where the function change quick, and discretize less when the function change slow. Okay. If I have a function that change very quick, like this, and I have two sections, okay, what happened? Trapezoidal method may overestimate the area, right? Okay. But if I discretize more, when it change quick, and discretize a little bit less when it changes less, then it's more accurate. This kind of discretization, we got it automatically from Runge-Kutta framework. Or you can use domain prims. Okay? This kind of integration we call adaptive step size. Alright? Where do we use that integration? Oh, let's take a look at this method. This is not freezing method, right? It's a flow integration to get mass flow rate based on what we see. With the flow, during the flow, how much is WL? Okay. So basically, we try to do this form. Okay, this form of integration requires the knowledge of that one that we just did. Plug it in. What about HLOS? Yes, where does HLOS come from? Do we have it? What is the full name of HLOS? Okay, do we have it? At what point in time that we have it? Do we have it before do RKF45 or after RKF45? Oh, come on. We get it right up front. Okay? Based on causal relationship. Gomez et al. From Gomez et al., we get HLOS. We have it right up front. Okay? We need that. If we don't have that information, doesn't work. Nothing work. Nothing work at all. Alright? What about VS? Yes, do we have it? Before or after? RK45.
Yes, we had it before.
Before. We have right up front, VSL plus VSG, right?
Yeah.
New, that is, where does that come from? Frequency. Okay. So this thing is going to tell us if we have frequency and slug length, they are related, right? VTB have something to do with LU, right? You remember that? Okay. So this will tell us the output of WL. Okay. And it should be the same. So I assume that LS equal to 30 diameter. WL output is 1.217. Okay. What is the WL, initial WL that I put it in? I put it in 1.0, 134. What I get it out is 1.2. So it doesn't match. Right? Something is wrong with that. Okay. So now I ask, yes.
So in that case, the slope length is too much, or because we're integrating in that case from a section.
What do we adjust? Which one is too much, right? That make we overestimate WL. There could be several things, but in this case, we adjust WL. We adjust LS. Instead of adjust WLS, we can adjust frequency. So it depends on which variable that we take it for granted. Which one do we believe? If we believe in frequency, we adjust slug length. If we believe in slug length, we adjust frequency. But this time, I adjust slug length. I do it again, use LS equal to 0.01. And do everything. I calculate WL. I get WL of 0.493. Doesn't match either. Okay. Then I plot LS in x-axis, WL in y-axis. Okay, we have two dots. Okay, if I use 30 diameter, I get about 1.2. If I use something small, I get about 0.5. Okay, and what do I need? I need the view output of 1 point something, right? So I can read from my graph. What should be the next case? WL target is 1.015. So I go there from this linear line, go down. Hey, the next case should be 0.55 meter. Okay? So I have two dots, then use linear interpolation. Based on the target, we know that, okay, we should use LS equal to 0.55. Put it in, okay, then I get something close, but not exact. What is the actual target? 1.0134. What do you get? 1.0, not 134, but it's 1.5. So that is a little bit too much. Just a little bit too much. What do I do? Okay. I do it again. Use LS equal to that much and that much. So I have two dots and use linear interpolation to get another guess. Okay. Then the next guess based on linear interpolation should be 0.5486. Okay. From that, I get it matched. Same result as the input WL. So in this case, we play or we adjust LS until we have mass balance. Okay. So this means we trust. We trust this formula. So this means we trust this formula, but we don't trust this formula, 30 diameter. Oh, where's my 30 diameter? Anyway, so we don't trust that it's 30 diameter, but we trust the slug frequency. What is a good reason for that? You have good reason for that? What is the slug frequency value that I got? It's about 5 Hertz. Okay, 5.29 Hertz. 5 times per 1 second. Okay, so if I wait 1 minute, 300 times or something. So typically, slug frequency has less error than slug length, because what they do is they can count how many that they see per 1 minute, right? Or they can take a video, slow it down, and count how many per 1 minute. Make sense? But for slug length, you have to take a picture of something that is moving and find out what is the length. That's a little bit challenging. This means you have to scale over there and see what is inside the pipe. Not as easy as slug frequency. Okay. In other lab, they have capacitance sensor based on the capacitance of the fluid, electrical capacitance. When it flows, it pick up the signal and it output different voltage. Okay. So based on how that curve fluctuates, they can tell how much is the slug frequency. Good. Slug frequency change with time, but on average, it's not like 1 plus 1 equal to 2 or something like that. It's not that precise. It has some chaotic in nature. It is chaotic in nature, but on average, it is deterministic. Okay. Think about it like velocity in the turbulent flow. At one location in turbulent flow, we cannot tell what is the velocity at a certain instant in time. It may move up or down radially, right? But on average, radial velocity is 0. Okay? Same thing. It is a chaotic system. A little bit change in the initial condition, it change the result. But on average, we can do the measurement. Okay. All right. Once we have the match, we can do it other way around. Like, let's say we trust 30 diameter, but we don't trust slug frequency. What do we do? So we set 30 diameter, right? Then slug frequency we calculate it. So we calculated how? What did the book say? Or the book doesn't say anything like that.
Because we know VTB.
VTB, yes, we know VTB. We trust VTB too. Okay, let's go back a little bit. So we have to do the integration, we need the point that we stop. When do we stop? What is the film length? Previously, we get total slug unit length from VTB over nu, right? That is total slug unit length. But this time we don't have nu. Okay. What we have instead of nu is we have the length, slug length. Okay. Do we have film length? I want to think about it later in the quiz next time. What did the book say? It didn't tell you anything. In the book, at the end of this page, page 98, it tells how to do the calculation. Okay. This calculation use adjust LS until we have a convergence. Okay. Calculate slug frequency from closure relationship, page 98. If we don't want to calculate slug frequency from the closure relationship, what do we do? The answer may be from equation 3.110. Okay. In 3.110, I get LF equal to LU minus LS, or VTB over LS minus LS, or not BS, but the frequency. So we can calculate. Can we calculate TS?
Yeah.
Yes, we can, but that doesn't help much. Let's think about it later. Okay, but right now you know how to adjust slug body length. Okay, until we have mass balance. Okay. If what I did is, if you trust the slug body length, okay, you trust that okay LS is correct for sure, then you stop the integration whenever you have mass balance. The RK45, previously we know LU, right? That's how we know where to stop. Okay? But when we don't know LU, we can stop wherever it makes the mass balance. So what's gonna happen is we solve ODE, we get the next point. Right at the next point, then we calculate WL. Hey, WL that we get. Can we calculate WL when we have just a short section of the film? Yes, we can. We can always do this, right? VLTB, HLTB. VLTB still come from X, right? We know HLTB at that location, we can always get VLTB. Make sense? We can get the velocity, we know the whole up, then we can calculate that integration, and we can add into that equation and see if we have enough WL or not. If it's not enough, we keep solving RK45. Do the integration. Hey, I don't get enough, I do more. We stop when we have mass balance. Okay? The film length, this time we adjust the film length until we have mass balance. Then film length plus slug length equal to slug unit length. Then you do something from slug unit length and VTB, you get frequency. Okay? That's another way around. Alright? Okay. The tricky part here is about RK45. Okay. Last time we tried to talk about it a little bit. but I forget to multiply by delta H or something, that's why it doesn't converge. Now we will revisit that.
Any question before we go to the numerical method? Not yet?